Today we will discuss regarding the instruction set and the programming of 8085 microprocessor. As we all know, instruction cycle is the time taken by the microprocessor to fetch, decode and execute any instruction. Now we will discuss the instruction cycle of LDA 16-bit address, which means load accumulator direct from memory. In this particular instruction, the contents of the specified memory whose address is given in the instruction is copied to accumulator register or the A register. If you want to code LDA instruction, it requires 3 bytes and number of machine cycles in this LDA instruction cycle are 4. The first one, opcode fetch, followed by 3 memory read machine cycles. The 3 of them are for the fetch part and the last memory read machine cycle corresponds to execute part. As an example, let us consider that the 16-bit address is C080H. So LDA C080H means the content that is available in C080 will be copied to A register. Say for example, the LDA C080H instruction is coded from memory location 2050 onwards. In 2050 we have the opcode 3A. In 2051 it is the low order byte of the address 80, and in the third byte it is the high order byte of the address. So whether it is 16-bit data or 16-bit address in 8085, we have after the opcode the low order byte that is coded first and then the high order byte. Say if the memory location C080 consists of 43, then after LDA C080 the content of C080, that is 43, will be copied into A register. Now let us discuss the timing diagram. As we have already discussed that we have 4 machine cycles. First one is the opcode fetch with 4 clock cycles, followed by 3 memory read machine cycles, each of 3 clock cycles. So in the first machine cycle, especially in the first T state of opcode fetch cycle, the contents from program counter, which are now assumed to be 2050 as far as this example is concerned, will be output on the address bus. High order address 20 are put over A15 to A8 and low order address 50 is put on the low order address lines AD7 to AD0. During the same T state, the ALE is activated, which latches the low order address and is made available to the external devices. Once the memory location is selected, after T1 state, it is the read signal that is made active, and this read signal, when it goes low, will activate the memory device and will release the content of 2050 memory location, which is nothing but the opcode of LDA, onto the data lines. Internally, the program counter is automatically incremented to point to the next address. During the third clock cycle of the first machine cycle, the opcode that is released on the data lines is brought inside the instruction register of the microprocessor, and the read signal will also become inactive, and again Here the multiplexed address data bus is shown to be in the tri-state condition. In the fourth T state, the decode operation takes place, and what is available on A15 to A8 is undefined during this clock cycle. So at the end of first machine cycle, the decode operation is over, the opcode has been fetched and decoded. So it knows, the microprocessor knows that it is LDA instruction, and it encodes the remaining 3 machine cycle automatically. So in the next machine cycle, it will be the memory read machine cycle, because the low order address 80 must be read from 2051. The address 2051 is already available with the program counter. So in the beginning of the next machine cycle, that is during T1 state of the next machine cycle, that is memory read machine cycle, the address 2051 will be output on the address bus. So the similar set of actions takes place, that is ALE signal will be high during T1 state, which will latch this 51 low order address bus, and then during the T2 state it will be the read signal again becoming active. Now it will be the turn of 80 to be released onto the data lines. Meanwhile, the program counter will be automatically incremented by 1 internally to point to the next address 2052. That completes the next machine cycle, that is memory read machine cycle. But now, where is this 80, that is the low order address that is released, be stored inside 8085? It will be stored in the temporary register Z, as shown here. Because the decode operation was already over during the first machine cycle, the microprocessor very well knows that after the first memory read machine cycle, it will be the memory read machine cycle to read CO, that is C0, that is a high order address from 2052. So 2052 will be output on the address bus, the ALE will be again released and 52 will be latched. Then we have the read signal that is coming out during T2 state, and PC is again now incremented internally by 1, and now it is pointing to the opcode of the next instruction, because LDA instruction requires only 3 bytes. So now the C0 that is released on the AD bus will be taken on into another temporary register, that is the W register. So high address byte is taken in W register, low order address byte is taken in the Z register. So at the end of these 3 machine cycles, the fetch operation is complete. But in order to completely finish off this LDA instruction, yet the execution part is not over. So to complete the execution part, it is required that the content from the address C080 must be read. So C080, which is now available with WZ, will be read in the next memory read machine cycle. So the last machine cycle, which is the execution part, is different from the previous memory read only in the sense that the address will not come out from the program counter, but it will be from WZ registers. So you can see still the program counter is pointing to the opcode of the next instruction, and those contents are not disturbed. So in the last machine cycle, which is the memory read machine cycle, again the address will be output on the address bus from WZ registers, and the similar set of actions take place. So C080 is put out, means this memory location is selected, and then again the read signal, when it comes, it will just release that 43 onto the data lines, and because it was decoded earlier, this data will be written into A register. So now you can see that the last memory read machine cycle corresponded to execution part, and therefore the address was not sent out from the program counter as usual. So it is very clear here that the program counter is affected only in the fetch part of the instruction cycle. And as far as LDA is concerned, the last machine cycle, the address is sent out from the temporary registers WZ, where the bytes were fetched and stored earlier. In the STA 16-bit address, it is just the opposite of LDA as far as the last machine cycle is concerned. So if LDA has last machine cycle as memory read, STA 16-bit address, which means store accumulator direct to memory, it will actually perform a memory write machine cycle in the last operation, because store operation is a memory write operation. So the contents of accumulator will be written into the specified address. As far as the LDA and STA is concerned, the number of machine cycles are 4. The first 3 are exactly the same, and the last one is the memory write instead of memory read. If you say STA C020 with A is equal to 22, now after STA C020, whatever was present in C020 will be overwritten by the contents of accumulator. As far as this example is concerned, it is 22 that will be available in C020H after STA 16-bit address is executed. That is, after STA C020 will be executed. Say, suppose 37 is the content of C020 earlier to the execution of the STA C020 instruction, then it will be replaced by 22 after the instruction execution is over. The timing diagram, I'll just have a quick look out at the 3 machine cycles. You can easily understand how things are changing. It is just exactly the same as we discussed in the case of LDA instruction. The second machine cycle, the memory read in order to read the low order address byte. The third machine cycle is again memory read in order to read the high order address byte. They are exactly placed in W and Z registers as before, but now the last one is a memory write machine cycle. Of course, the address will be sent out from WZ registers, but instead of read signal, it will be the write signal that will become active, and the 22H, that is contents of accumulator, are already put on the database during T2 state, which will be written into the memory location whose address is already available with the address lines. That is, content of A 22H will be copied into C020. That is the difference between the load and store operators. Next one is the LHLD 16-bit address. So here you will have load HL registers direct. So contents of the specified address will be taken on into the L register, and the contents of the next address will be taken on into H register. So number of bytes required to store this instruction are 3. Number of machine cycles are 5. If you just compare LDA instruction and LHLD instruction, the one more machine cycle has been increased because it is going to perform 2 memory reads in the execution part, and in LDA instruction it was only 1 memory read instruction in the execution part. That is the difference. So if it is LHLD 2050 with 2050 consisting of 37 and 2051 memory location consisting of 46. So 37 will be taken on into L register and 46 will be taken on into H register after execution. Just the opposite is the SHLD instruction, which means store HL register direct to memory. You can specify any 16-bit address in the range 0000H to FFFFH in the place of 16-bit address. So here the contents of L register will be stored in the specified address and the contents of H register will be stored in the next address. The difference between LHLD and SHLD is the last two machine cycles, which were memory read machine cycles in the case of LHLD, but now they are the memory write instructions. So store operation involves the write operation in the execution part. Load operation includes the read operation in the execution part. It is just a similar example that has been taken. So if L register is having say 37, that will be stored at 3050, and the contents of H 46 will be stored at 305. Now coming to the instructions involving M. RD represents the destination register. M, any memory location amongst the 65,536 memory location, but the address of M is specified by one and only HL register pair. That is the meaning of M here, right? So M means any general memory location, but when we say memory location, there should be an address to specify the memory location, and therefore where this address the microprocessor will look into, it is the HL register pair always. That is the way it has been designed. So if at all any instruction it comes across involving M, it will look into HL register pair for the address of this M, and whatever 16-bit number is available in HL register pair will be treated as the 16-bit address of this M at that moment. So we have three instructions shown here with move RD comma M. That means your memory is the source. Next one is a move M comma RS, where memory is the destination, and another one is move immediate M comma 8-bit data, where 8-bit data will be loaded into any memory location whose address is specified in HL register pair. So that is the meaning. There is M represents a memory location whose address is pointed by HL register pair, or microprocessor gets address of memory location M from the contents of HL register pair. That's all what we were discussing. The first one, move to register from memory. From the memory, you can specify any of the registers as destination. So number of machine cycles are 2. Opcode fetch and memory read. Of course, the memory read operation corresponds to execution part. Say for example, if you write move B comma M, while this instruction is executing, say suppose HL register is 6780, that means it consists of 6780H, then naturally 6780H itself will be treated as the address of M. So now from which location the contents will be transferred to B? It is from the contents available at 6780 address that will be copied into B. So at 6780 you have 25, that means after the instruction move B comma M, it will be 25 copied into B register. You can easily see that the 6780, the address is specified by HL register pair, and the content 25 will be copied into B register. So after execution, the register B consists of 25H. Just the reverse, we have move M comma RS. It is also similar to move RD comma M. Again, here we will have memory write as a second machine cycle instead of memory read, because it is write operation with respect to memory. So if say accumulator consists of 55 and HL register pair consists of 5080, that means now the address of M is 5080. Contents 55 from accumulator will be copied into memory location 5080. So it is a memory write operation. So M is nothing but the location 5080 because it is pointed out by HL register. Now after execution, the contents of A55 will be copied here. Therefore, contents of 5080 will be equal to 55 after move M comma A instruction. Next one is move immediate M comma 8-bit data. You should see here very clearly that to read the 8-bit data, once we have the memory read machine cycle, and it has to be written into the memory again, because as far as this particular instruction is concerned, the 8-bit data has to be copied into the memory location. So we require 3 machine cycles. The first 2 are the part of the fetch operation and the last one is part of execution. As an example, move immediate M comma 6 AH. While this instruction is executing, if say HL consists of 6000 H, that means M is now the memory location 6000, and now we have, say, suppose some data written into 6000 H that will be overwritten by 6A after the instruction division is complete. Next one is another LDA instruction, but here we have that letter X to indicate it is extended a register that is involved. RP represents the register pair, and we call LDAX as load accumulator indirect. The words direct and indirect correspond to the addressing modes that we'll be studying later. So only 2 instructions are available here, LDAXB and LDAXD. There is no as such LDAXH instruction or LDAXSP instruction available in the instruction set. So what does this LDAXB mean? Contents of memory whose address is specified by BC register pair are copied to A register. So it is particularly for BC register pair. So naturally, the BC register pair holds the address from where the contents will be copied to A register. Number of machine cycles are 2. Say suppose while this instruction is being executed, BC register pair consists of C080. So naturally, now the contents of C080 will be copied into accumulator. After execution, therefore, accumulator consists of 42. Just the reverse of which is the STAX RP. Again, 2 instructions are available, STAXB and STAXD. Say suppose we take the example of STAXD, that means the contents of accumulator are stored into memory locations whose address is shown by DE register pair. Now it is a memory write operation in the